In this video, we continue with chapter 7.4, where we're looking at applications of eigenvalues and eigenvectors. So in this video, we are going to see how we can use a matrix equation with the corresponding eigenvalues and eigenvectors to solve a system of first order linear differential equations. And this is the kind of setup we would need to use if we're programming a computer to solve these equations for us, or building out a computer program that involves differentiating differential equations of the first order. You can see, you could write corresponding code for second order and so on. So recall that a system of first order linear differential equations has this form. Because it's linear, our exponent is 1 on all the y's, and then our coefficients are the a1 through ann here, corresponding with the n equations of the differential equations. And then the initial conditions come in when we plug in 0 for the time t, or whatever our variables we're using over here, to each of the y's. And so we're going to call the initial values the c's. So we've got c1 through cn here. And that corresponds, I think, to the nomenclature and symbols you used in calculus, c's for constants. So each yi is a function of t, and then the derivative, we're going to say, is the derivative of yi with respect to t. So we'll use the Leibniz notation here, dyi, with respect to t, with the dt there in the denominator. So this is considered a linear system because the y primes, y1 prime through yn prime, is a linear transformation of y1 through yn. By linear transformation, we mean the coefficients here for all the y's is 1. Our matrix A here is a matrix of all the coefficients from the n differential equations. And so we can find y prime of t by calculating A, the matrix of the coefficients, multiplied by y of t. And in this case, y of t is this vector of y1 through yn. And so this A is all matrix of constants, and the y is a vector or column matrix of variables. So these are the first order differential equations because they contain just first and not higher differential values or derivatives. So let's look at solving this system. So in this system, we've got y1 prime is lambda 1 y1 plus zeros for the coefficients for y2 and y3. y2 prime has got zeros for the coefficients for y1 and y3, and lambda 2 multiplied by y2. And then y3 prime has zeros for the coefficients y1 and y2, and lambda 3 y3. Remember, all of the initial conditions are c's, so y1 of 0 c1, y2 of 0 c2, and y3 of 0 c3. So from calculus, we know that the general solution to y prime of t equals k of y of t is in this exponential form. You remember separating out the dt's. So if I write that out how you did in calculus, it was like dy dt equals k times y of t. And then remember, you had the dt over here and the dy over there. So you ended up with like a dy over y of t equals k dt. And then when you integrate both sides, that's where you get your y equals c e to the kt that we have up here. Because when you integrate, you get a ln, and then to get the y by itself, you have to exponentiate the right side. So I think you did this end of Calc 1-ish. So near the end of the semester in Calc 1, you did this, and maybe again in Calc 2 as well. All right, so then we know our solutions are going to end up in this form where our coefficients for the matrix end up here, and the exponents is our k's. And in this case, our coefficients are these lambdas, lambda 1, lambda 2, and lambda 3. So our solutions are in the form y1 of t equals c1, that's our constant corresponding with the initial value, e to the lambda 1t, y2 of t equals c2, e to the lambda 2 of t, and y3 equals c3, e to the lambda 3 multiplied by t up there. So let's take a look at a little more involved example. So here's an example where we've got y1 prime through y4 prime, and they each equal a different constant multiplied by y1 through y4. So the solution is going to be, we know in this form, y equals c e to the kt. So then we just take our constants and plug those in for the k's. So y1 here is c1 e to the 7t because of the 7 here in that differential equation. Y2 is c2 e to the 9t because of the 9. And then in the differential equation for y2, y3 is c3 e to the negative 7t because of the negative 7 in the differential equation for y3 prime. And y4 is c4 e to the negative 9t because the negative 9 in the differential equation for y4 prime. So we see the constants end up in the exponent because of what we know from calculus. When we rearrange and integrate these differential equations, we end up in this y equals c e to the kt form. So let's do now a slightly more complicated one with multiple constants and a sum here. This is what we've been building up to. So we want to solve this system here where y1 prime is y1 plus 2y2 and y2 prime is 2y1 plus y2. So we start by building our coefficient matrix A here. So this is matrix A, and it corresponds just with the coefficients in each equation. So because y1 prime is got a 1 here with the y1 and a 2 with the y2, the first row of matrix A is 1, 2. And then because y2 prime has a 2 and a 1 for the coefficients on y1 and y2, the second row of matrix A down here is 2, 1. We multiply this by our y1, y2 variables to get ay. And so we want to find the eigenvalues of A. So they are -1 and 3. It doesn't matter which we call lambda 1 and which we call lambda 2. You can see my SIMPy calculations over here. And they're each come up with multiplicity 1. They just come up once each. And then the corresponding eigenvectors are -1, 1 for eigenvalue -1, and the vector 1, 1 for eigenvalue 3. So we diagonalize A using matrix P, which is just the matrix with the columns that are the eigenvectors. So it doesn't matter which values you pick first here. You can actually see here, because we can have scalar multiples for the eigenvectors, notice in my notes here, I've got 1, -1 for x1, but over here in SIMPy, I've got -1, 1, because remember the eigenvectors can be scalar multiples. So that's why you see this difference here in our matrices for P, whether the way I did it over here on the typed on the left, the type solution, versus when I calculated in SIMPy. But in the end, it doesn't matter because when you diagonalize and multiply P inverse AP, we get the same matrix, -1, 0, and 0, 3. So remember, you can use the scalar multiples of the eigenvectors. And so that's why when we do the diagonalization in SIMPy, we don't necessarily get what we get if we do it by hand because of the scalar multiple option there with the eigenvectors. And it's totally fine. If you do something by hand and then check in SIMPy and it looks different, just stop and check, are those eigenvectors scalar multiples of each other? And in this case, the scalar multiple is -1 to flip the sign there. So as long as your eigenvectors in SIMPy are scalar multiples of what you get by hand, everything works out just fine. You don't actually have any issues. It's just the difference of scalar multiples. All right, so we ended up here with our P inverse AP matrix, our diagonal matrix. And so we're going to use that now. So the solution of the system W prime, which is P inverse APW, is W1 equals C1 e to the -t. That's because our first eigenvalue Lambda 1 here was -1. And then our second eigenvalue is 3. So our second solution here is C2e to the 3t because lambda 2 is 3. So we return to the original system by applying the substitution here, y equals pw. So you can say, okay, here's matrix P. And if you use the other matrix P, you can see it's not going to make a difference. We're just going to reverse, which is y1 and y2, because remember the difference here was the scalar multiple here. So here's matrix P multiplied by W. And when we do that, we get these two equations, which end up down here, how we construct our solutions, y1 and y2. And you can see the W's are just the C1 e to the -t, and the W2 is the C2 e to the 3t. So again, if you use different scalar multiples of the eigenvectors, it doesn't change the overall relationship in the equation. You can always divide through by a scalar with equations because you divide through on both sides and it doesn't change the results. Okay, let's look at 3 equation examples. So in this example, we've got y1 prime, y2 prime, and y3 prime. And when we take their coefficients to construct matrix A here, it ends up being a triangular matrix because of the basically 0, y1 in the first or in the second row and 0, y1 plus 0, y2 in the third row. All right, so y prime is equal to matrix A times y, which is the column vector y1 through y3, and that works out to be a y. And so we're gonna use our eigenvalues. So on the next slide, I've got my SIMPy calculations. So you can see each of my eigenvalues has multiplicity 1, and my eigenvalues are 1, 2, 3, and then here's my eigenvectors. And so remember, it doesn't matter if we use scalar multiples. So like this eigenvector gets doubled in the typed up example. And so those values are 7, 8, and -2, I believe. -7, 8, and +2. Sorry, I mislooked. And so if we come back here, we see here are our 3 eigenvalues. And they correspond, give or take, the scalar multiples to what we find in SIMPy. And so eigenvalues are 1, 2, 3. And so when we set up our matrix P with the eigenvalues as the columns of matrix P and calculate P inverse AP, we get our eigenvalues here on the diagonal, just what we expect. And the solution to the system, W prime equals P inverse APW, is to have W1 equals C1e to the t because our first eigenvalue is 1. The second solution, W2, is C2e to the 2t because our second eigenvalue is 2. And the solution to W3 is C3e to the 3t because our third eigenvalue is 3. So here's my calculations from SIMPy, and you can see when I diagonalize, even though, they actually end up with the same scalar multiple of our eigenvalue. So it works out just the same here. Sometimes you'll be off by a difference of a scalar multiple. It doesn't affect the final result where you still get this same matrix with the eigenvalues on the diagonal. And here's the rest of our solution. So here's our W's we just found in the last slide. C1 e to the t for W1, W2 is C2 e to the 2t, and W3 is C3 e to the 3t. Now we come back to our original system by multiplying by the W1, W2, W3 vector here to get the structure of these equations. Just a standard set of variables here because we don't want to write out the C e to the kt every time. So when we go through the calculation, what it gives us here are the formats and how the coefficients go with each of the W terms. And then we just replace them with the C e to the kt terms here. So we get y1 is c1 e to the t, because that corresponds with w1 minus 2. And then for w2, we know that's c2 e to the 2t minus 7 c3 e to the 3t. So you could do this multiplication here if you didn't want to write in kind of these dummy variables, w1, w2, w3. You could just do it with your c e to the kt values. There's no reason it wouldn't work just fine if you're multiplying by hand. So the w's are just sort of extra there for to stand in, but it's not necessary because you could just as easily write these out. So y2 has no w1 value, so we just have c2 e to the 2t plus 8 c3 e to the 3t, and then y3 just has a single 2w3, which is 2c3 e to the 3t. Okay, so that's our solution here of the system of first order linear differential equations we solve for y1, y2, y3. In the next video, we are going to see how to work with quadratic equations to solve optimization problems for quadratics. And so that'll be the last set of applications for chapter 7.